let fx be a polynomial over a field, then we say that f admits a repeated root. Now, as the previous theorem, I mean the Kroneker's theorem suggested that f need not have a root over the field itself, it can have a root over some superior field, right? So therefore, we can define the notion of the repeated root in this way, that so we say f admits a repeated root if t repeated root, let me define it in this way, admits a repeated root alpha if t minus alpha squared divides f of x, sorry, f of t in some field E over F which contains alpha. Yeah. Okay. What I'm trying to say here is that if I can write f of t as t minus alpha squared times some g of t, but this division did not occur over the field itself, I am allowing it to occur in that superfield which contains the root of f. Got it? Fine. Now recall, I'm telling recall, but I don't think I had given the definition, or I might have given the definition of what we call the derivative. Okay, the formal derivative. Now, if you have studied calculus, you know what the derivative of a polynomial typically is. But since in algebra we do not deal with such analytical structures, so what we do is that we define something in analogy with the formal derivative. Okay, so let d be a map from ft to ft via what I do. I take the element of the form t to the power n and I map it as n times t to the power n minus 1. Okay. In other words, what I'm trying to do, so I will take this polynomial a n t to the power n ranging from say 0 to k, and I'll map it to summation n times a n t to the power n minus 1 n ranging from 1 to k. Yeah, the basic derivative, the basic notions of derivative. Fine. And what I claim the following claim. Now this is something you should have learned when you have studied polynomials over in single variable calculus. And the claim is the same as we studied there, that let f be a field, and let f of t be a polynomial over ft. Okay. Let um, let E be the field over which, let's say, f splits. Okay, we know by Kroneker's theorem that happens. There exists a field containing f over which the polynomial will split. Right. In other words, we can get hold of a field which contains every root of f. So what I claim is that then f has no repeated root, if and only if the GCD of the polynomial with its derivative is 1. Okay, got my point? Now, why am I discussing it over a field over which the polynomial splits? So that I can make sure that I can talk about the existence of such roots. I could have easily omitted this part, okay, and I would immediately have had a discussion about if has no repeated root if and only if this happens. But still, in the course of the proof, we will need to get hold of such a field where the repeated root, if exists, should lie. Okay, so in some sense, I have just taken up a field over which will contain every root of f, and I can talk about it in that field itself. But nevertheless, we do not require in the hypothesis itself a field over which f splits. Fine, and the proof is pretty obvious. Okay, and it's sort of very intuitive, and our proof will be sort of very intuitive as well. Okay, now if you recall the notion of definition, what we had said that over a PID, the GCD is basically the generator of the principal ideal of the ideal generated by two polynomials. Right? We had discussed this in some previous lecture, and this is accordance with whatever we have here. So what we do, so let the ideal generated by ft and the derivative of ft be generated by some qt. Okay, then we show that qt itself is the constant polynomial one. Okay, this will do. Fine. Okay, so what we want to do is that let's say and this qt should be having degree greater than 1. Okay, we assume it to be having degree greater than 1. Okay, yeah. Now why do we assume this to be having degree greater than 1? Because at least I need to talk about the derivative, right? Derivative of the polynomial f. Now it is pretty easily observable that if f and g is generated by some polynomial p, then p must divide f and p must divide g. Now obviously, if I am talking about some root, f needs to be of degree at least 1. In that case, g will be of degree 0, right? And if f is linear, then f can obviously not have any repeated root, right? This is pretty obviously understandable. Getting my point? And if we talk about the derivative of f, then the degree of the derivative is basically 1 less than the degree of f, right? So if so, since here qt divides both ft and the derivative of ft, I'll basically require the degree of qt to be greater than 1 or at least 1. I can do this. Fine. Now let let E be a field which contains a root of qt. Okay, I was assuming that I would like to talk about the roots of f directly. That's why I gave this hypothesis. I don't think we'll require this. So let me remove this one now. Okay, we don't require this. Okay, fine. Yeah, let's come back to the proof. All right. So let yeah, which contains a root of qt. Okay, then let the root be alpha, which implies that q of alpha is 0, and equivalently speaking, x minus alpha should divide qt. Right now, since qt divides ft, this implies that I can write ft as x minus alpha times some gt, right? Then what should be the derivative of ft? Then see, by the way we define the derivative, I can also have the Leibniz rule in hand. Okay, that is the rule for the multiplication. So the derivative of ft should be x minus alpha times the derivative of gt plus the derivative of x minus alpha times gt. So that will just be gt, right? But qt, it divides the derivative of ft as well, right? So that implies that the derivative of f at alpha should be 0, right? But that implies g of alpha should be 0. That implies I can write g of alpha, or rather g of x. Oh, no, I took t, right? So I can write g of t as t minus alpha times some h of t. But this means that my f of t, which was t minus alpha times g of t, this is t minus alpha squared times some h of t, which implies that t minus alpha squared divides f of t, which implies that f has a repeated root. F has a repeated root. So what we conclude from here is the following: that um, if the GCD is not 1, that is, see, if the GCD is exactly a constant polynomial, since we are over a field, then I can obviously make it to be 1, right? The ideal generated by any unit element is equivalent or rather equal to the ideal generated by 1. That's why I'm choosing a non-constant polynomial. That's why I've chosen the degree to be greater than or equal to 1. So what I've chosen is that, or rather what I've proved is that if the GCD of ft and its derivative is not equal to 1, then f must have a repeated root, right? So you can simply take the contrapositive of this to have one part of the proof, right? That is, if the GCD is if it has no repeated root, then the GCD should be 1, right? Now let us talk about the converse. Converse. Okay. So what we assume is, suppose ft has a repeated root, right? This implies that there exists some field E over f containing some alpha, such that t minus alpha square divides f of t in et. Yeah, so we required such a field which contains a root. Yeah, okay, it will suffice, right? Existence of only the repeated root will do. So rather leave the hypothesis of getting to a field over which f splits. Fine, right? Fine. So therefore, I can write my f of t as t minus alpha squared times some gt. So that means the derivative of f of t, what it should be? It should be 2 times t minus alpha times gt plus t minus alpha squared times d of gt, the derivative of gt, right? So I can write this as t minus alpha times 2 gt plus, so this is t minus alpha times the derivative of gt, right? Now what do we conclude from here? Therefore, the GCD of ft and d of ft is equals to t minus alpha, which is obviously not equal to 1. Now this GCD is calculated in et, right? But observe that if it's non-trivial over et, recall we had proved that if the GCD of f and g is equals to some k in f, then it's k over any field containing f, right? Therefore, if it's non-trivial over any field containing f, it should again be non-trivial uh, over the field over f itself, right? Therefore, yeah. So I guess we had proved it somewhere in the last to last lecture. Yeah. Okay, I directly got hold of this here. That is the GCD of fd over f is same as the GCD of fg over e, where e is some field containing f, right? Wow. Okay. So fine. So that implies that the GCD of ft and the GCD of its derivative is not equal to 1 over f as well. Because if it was 1 over f, then it should have been 1 over et. Right? Fine. And this gives the proof. Right? Okay. Fine. Yeah. So what do we conclude from here is that to check the existence of repeated roots, what we need to check is the GCD between the polynomial and its derivative and its formal derivative. Right? Okay. Fine. Yeah. Now let us discuss a very important notion. Or rather, we are gonna, now we are trying to sort of enter into the notions of finite fields. And so let us start. So what is the first example of a finite field? Okay, so we have discussed enough about polynomials. It's a bit of time to get into the notions uh, of finite fields. But before that, let me talk about a very simple thing. Okay. Uh, so theorem: if f of t is in ft is irreducible over f, then ft has repeated roots if and only if the derivative of ft is 0. Okay, that is if a polynomial is irreducible over some field and it has no and it has a repeated root if and only if its derivative is 0. Okay, fine. Let us prove this first and then we will give an important insight to it. Proof. See, if f is irreducible, then so if f is irreducible, then the GCD of ft and dft should be either 1, okay, or it should be the whole of ft, right? Right. Now, degree of dft should be less than the degree of ft, which implies that ft does not divide dft, right? Which implies that the derivative should be 0. Yeah, got it? Okay, fine. Let us move on. Can I say the same over finite fields or fields with characteristic of some prime? Can I do that? Yeah, try it out. Okay, check and try it out. Okay, just choose a polynomial. Okay, what I'm trying to say is the following: can this hold over fields of characteristic non-zero? Okay, fine. Right. Now let us move on to the notions of finite fields. Okay, let us talk very briefly about finite fields, and we'll talk about multiple notions regarding finite fields. Okay, as much as I can, I'll try and explain everything which is possible in terms of finite fields. Okay, yeah, but just give me some time. Okay, I think there's a problem with my laptop. Yeah, fine. Okay, yeah. So this is the question I gave. Fine, right. Now, what we want to do is to get hold of the notion of finite fields. Okay, and the motivation is basically, can there exist fields of finite order? Okay, of finite order, and if so, what can be its analyzable properties? Okay, a very easy question to talk about. Okay, let's see. Okay, see, we already have a very important example of finite fields, which is ZP. Right, this is a finite field. This is a finite field, as we all know. Okay, now let us talk about the following things. Now, yeah. So so this is actually a theorem, but I am not going to pose it as a theorem. Rather, it will come up as a development of a theory in some sense. Okay. So let P be a prime. P be a prime. Then we often denote it as FP. FP is equals to Z mod P, which is isomorphic to ZP, is the field of order P. Okay, is a field of order P. Now, suppose let's say suppose F is a field. F is any field. Choose a map. Let J be a map from Z to F, such that J takes 1 and maps it to the unity of F. Okay, fine. Now see, you can easily observe that that is actually a ring homomorphism. Okay, this is actually a ring homomorphism. So we can readily talk about the first isomorphism theorem. How? So this implies that Z mod the kernel of J is isomorphic to the image of J, and the image of J must be a subring of F. Okay. Some things which can be immediately observed is that F is a field. That means an integral domain. Any subring of an integral domain is an integral domain. So this is an integral domain. Once it is an integral domain, I can say that this kernel of J must be a prime ideal. Must be a prime ideal. Once it is a prime ideal and it's a prime ideal in Z, right? So what can we conclude from here? That this implies that the kernel of J is either 0, and if non-zero, it's generated by some prime number P. Okay, got my point? Right. Now, suppose J is injective. J is injective, which means that the kernel of J is the zero ideal. Okay. In this case, we say that the characteristic of the field F is 0. Okay, fine. And furthermore, we can conclude that Z is embedded inside of F as a subring. Okay, fine. Now, if the kernel of J is some ideal generated by P, then that implies that Z mod kernel of J, which is equal to Z mod the ideal generated by P, which is isomorphic to ZP. This, what we have proved, is isomorphic to the image of J, which is a subring of F. So this is a field. ZP is a field, right? Therefore, this implies that ZP is embedded in F as a field. Okay, and in this case, we say that F has characteristic 0. Now, how the term characteristic has arrived? Let me see, and it is very clear. Okay, see. Observe that when kernel of J was 0, what does this imply? What was J? J would map 1 to 1, right? And what does kernel of J equal to 0 imply? This implies that you can keep adding 1 and you will never reach 0 until and unless you add 1 0 times, right? Unless you add 1 0 times, right? Therefore, in F, right, one can keep adding these ones and it will never be equal to 0. And in such a scenario, we call that F has characteristic 0. F has characteristic 0. But what if, uh, yeah, so what if the kernel is, so if the kernel of J is generated by some P, this implies that I can keep adding 1 P times, and once I add it P times, I'll get 0, right? Because J of 1 plus 1 and so on till 1, right? So this is 1F plus 1F and so on till 1F. So this is an element, so it's P times, right? And if the kernel is generated by P, so this should be 0. That means P times adding 1 in F will give you 0, right? Or P is equal to 0 in F in some sense. Whatever, in whatever scenario you want to talk about it. In this case, we say that the characteristic of F is P. Okay? Got my point? Right. So what do we conclude typically is that the characteristic of 0, so the characteristic of, sorry, not the characteristic of 0, the characteristic of the field F. So as we conclude that the characteristic is completely determined by the number of times I need to add 1 to get to 0, right? So therefore, this map defined by J is the only procedure to have a good definition of characteristic, which can easily be seen here, right? Therefore, for the characteristic of F, we have only two possibilities, right? Either it's 0 or it's some prime P, right? Right? So the characteristic of F can either be P or be 0. Once it is P, what we know that ZP is isomorphic to the image of J, which is a subring of F, and 0, when if it's 0, so Z should be isomorphic to the image of J, which is a subring of F. So either Z is embedded inside F as a subring or ZP is there inside F as a subfield, right? Fine. Okay. This is something which we can conclude. Now observe the following observation. Okay. If the order of field is finite, then the characteristic of F should be P. Why? As Z can no more be embedded in F, because Z is an infinite ring, right? The cardinality of Z is infinite. So if the field itself has cardinality finite, therefore its characteristic should be P. But if its characteristic is P, then what you can conclude? Then in that case, or rather in this case, what we can conclude is that the image of Jx should be isomorphic to Z mod Pz, which is isomorphic to Fp, or rather equal to Fp, the notation of Fp, right? Now F is a finite field, Fp is also a finite field. So if I consider F as a field which contains Fp as a subfield, what we call a field extension, then this should be a finite dimensional vector space over F, over Fp, right? We know that this if E over F is a field extension, that is E is a field containing F as a subfield, then I can talk about E as a F vector space. A very easy verification, you can do it on your own, right? So F over Fp is a finite dimensional vector space over Fp. Now, so in that case, what we conclude is that if it is finite, then that implies that the order of F must be some P to the power n, right? Why can I do this? Because if it is a finite dimensional vector space, then that means that if X is in F, then I can write X as some A1, E1, and so on and so forth till some AN, EN. But these AIs come from Fp, whose cardinality is P. So there are P of these AIs and N choices. So total number of choices for the elements of F should be P to the power n. So the cardinality of F should be order power of a prime, some integral power of a prime. So what we conclude, if the order of a field is finite, where F is a field, then the characteristic of F is P, where P is a prime, and what next we conclude is that the order of F should be P to the power n for some integer, positive integer, right? Okay. Now the next question which we can talk about in this case is that if I give you any prime, given P a prime, and a random positive integer n, then can I say, what can I say about the existence of a field F of order P to the power n? Okay. What we conclude is that if there exists a finite field, then its characteristic should be a prime, and the order of the field must be some power of that prime. But if I have given a random prime and a random positive integer, then can I say that there exists a field which is whose order is of the form P to the power n? And what we see is we can do so. Okay. So now this can be treated as a theorem that let P be any prime and n be greater than or equal to 1, then there exists a field F of order P to the power n. Okay. So let's see the proof. Okay. Now see, if n is equal to 1, then I can choose the field as simply ZP, right? So let n be greater than 1. Okay. Consider, now this is the important step, consider the polynomial phi t to be t to the power p to the power n minus t, which belongs to fpt. Okay. So I'm talking about a polynomial over the finite field fp. Okay. Now we know that given any polynomial over a field, there always exists a superfield of that field over which this polynomial will have a root, or rather it splits completely, right? Now, so that is what's called the Kroneker's theorem. So now by the Kroneker's theorem, there exists a field which extends fp over which phi t splits completely into linear factors. Okay. Now, what is the derivative of t to the power p to the power n minus t? It is minus 1, right? Therefore, the GCD of phi t and its derivative should be equal to 1, right? Clearly? Okay, why is the derivative minus 1? I should have, because this is the first time I'm speaking about such things, so I should make it clear a bit. See, because this is basically p to the power n times t to the power p to the power n minus 1 minus 1. But the characteristic of fp is p, which implies that p to the power n times anything is 0. So this becomes 0. So it's minus 1, right? Okay, since E is extending Fp, we can obviously talk about this, right? Okay, fine. Let's move this part. Now I go through these proofs slow so that you get time to think about yourself as well. And when I'm proving such things, there is no note in front of me, so it's like I'm also thinking as a, just like someone would have thought of proving these things. Okay, fine. So what does this imply? So recall we had proved this in this lecture itself, that if ft and its derivative is equal to 1 if and only if f has no repeated roots. F has no repeated roots, right? Fine. Now what does this mean? And we had also seen in some previous lecture that a polynomial will have at most its degree number of roots. Since we are working in a field over which the polynomial splits completely into linear factors, so this polynomial will consist each and every roots. All these roots are distinct, so there are p to the power n number of roots of this polynomial. Now what we do is that, sorry, now we claim that the set of all roots of phi t uh, forms a subfield, forms a subfield of E. Okay, let's try and prove this out now. Let alpha and beta be roots of phi t. Okay, then observe that alpha p to the power n plus beta p to the power n, right? I can write this as alpha plus beta, right? Why can I do so? Okay, let me explain this a bit now. Okay, there are certain things which I'm just skipping, but I don't want to skip these things. Okay, see, if I talk about alpha plus beta to the power p to the power n, then I can expand this using the binomial theorem. The binomial theorem holds whenever we are working over commutative rings. It's a field, so it's a commutative ring, right? So I can expand this, and alpha plus beta p to the power n, this should give you alpha plus beta. Why is it so? Because see, the coefficient should be of the form alpha p to the power n plus, uh, so I should have, or rather let me write the explicit form. So this should be of the form summation p to the power n r, alpha to the power p to the power n minus r, beta to the power r, where r ranges from 0 to p to the power n. But when r is not equal to 0 and not equal to p to the power n, all the coefficients are just multiples of p to the power n. So all of them will become 0 due to the characteristic, right? So this should just give you alpha p to the power n plus beta p to the power, right? But since alpha is the root of phi t, that means that alpha p to the power n must be equals to alpha, beta p to the power n must be equals to beta. So this must be equals to alpha plus beta. Therefore, what do we immediately conclude from here? That alpha plus beta p to the power n minus alpha plus beta should be 0, which means that alpha plus beta is also a root of phi t, right? Fine. Similarly, alpha beta to the power p to the power n, this is simply alpha p to the power n times beta p to the power n, since we are in a commutative ring, right? But then again, this should be alpha times beta. That implies that alpha beta p to the power n minus alpha beta is 0, which means that phi of alpha beta is 0. Therefore, alpha beta is also a phi, also a root of phi, and beta inverse is clearly a root, right? If beta is a root, right? You can just extend the minus 1 power and p to the power n. That's very easy to observe, right? Yeah. Okay. So what do we conclude from here is that therefore the collection of all roots of phi t forms a subfield of, say, so let us map this as k. But then what should be the cardinality of k? It should be exactly the number of roots. All the roots are distinct, so it should be exactly p to the power n, right? And this gives the existence of the field. Existence of the field. Yeah, got it. So therefore, given a prime and a positive integer, there exists positive integer n, then there exists a field of order p to the power n. Okay. Now let me give you a hint to a term. The smallest field corresponding to a polynomial f in which f splits completely into linear factors is called the splitting field of f. Is called the splitting field of f. So typically what we see is that in this proof that the splitting field of t to the power p to the power n minus t is the field of order p to the power. Okay, we will come up with a thorough discussion of these things, but for now let us just keep it as it is. Let us just talk about this as simply a a notion of what we call a splitting field. Got my point? Okay. Now, so once we have got the existence, so what we conclude is that there exists a field E of order p to the power n for prime p and n being a positive integer. Yeah. The next question which I should talk about is what can we say? What can we say about subfields of finite fields? Subfields of finite fields. Okay, fine. So yeah. So observe the following. Let the order of E be p to the power n. Okay, and let f be a subfield of E. Be a subfield. Okay. Then what we can say is that E should form an F vector space, right? So this should mean that E forms an F vector space, right? Okay. Therefore, what Shani says is that the dimension of E over F is finite. Okay. Therefore, so once the dimension of E over F is finite, now recall. Okay. So this is the notion of vector spaces, that if V is a finite dimensional vector space over a field F, and if the dimension of V over F is D, then V is isomorphic to FD. And how do we typically prove this? So choose any basis of V. Let's say alpha 1, alpha 2 till alpha n is a basis of V. Some basis of V. We know that basis need not be unique, but the dimension should. So choose an element of the form A1, alpha 1, and so on till A n alpha n, and map it to the coordinates A1 till A n. This will give you the required isomorphism. Okay, yeah, fine. Let's get back to our observation. Now, so what we conclude is that, so therefore, the dimension of E over F is finite. Okay, so this implies that E is E is isomorphic to FD for some D in integers, positive integers, right? But D is the dimension of E as a F vector space. Got my point? But then from here, what do we conclude? So this implies that the cardinality of E must be equal to the cardinality of F to the power D. Right? Now, characteristic of E is P, right? We're talking about finite fields. Right? So what do we conclude from here is that this means that the identity of E, if I add it P times, I'll get 0. I should get 0. Right? And the characteristic of F, so E is isomorphic to FD, right? So this means that if I add the identity of F P times, right, then again I should get 0. So this means that the characteristic of F should also be P. Very clear? So this implies that the cardinality of F should be of the form some P to the power n, right? What does this imply? This implies that P to the power n must be equals to P to the power m to the power d, right? Right. So what do we conclude from here? So this implies that m divides, right? Therefore, given a field E such that order of E is P to the power n and F in E is a subfield, then what do we conclude is that the order of F must be some P to the power n where m divides n. Clear? Got my point? You should be clear about this. Okay, fine. Now, my next question is that, so as we were asking in the previous part, that I can obviously talk about a field, whose order is p to the power n. But given a prime p and a positive integer n, can I construct a field? So we were always talking about equivalent statements regarding finite fields. Now, can I do the same here? Okay, can I do the same here? That is, uh, you know, uh, what I want to say is that is it sufficient? Is it sufficient to account for all divisors of n where E is a field of order e to the power n? Yeah, okay, of order p to the power n, to talk about all possible subfields. Okay, carefully watch this statement. You will get to see what I'm trying to do here. Okay, fine. So let's start up with this observation. Okay, what just happened? Uh, this journal is causing problem a bit. Okay, please just set along. So let m divide n, where the order of E is p to the power n. E is a field. Okay, consider the polynomial t to the power p to the power m minus t. Okay, which you can write as t times t to the power p to the power m minus 1. Right. Now observe the following. Now, so this is an independent observation. That is, since m divides n, that implies that p to the power m minus 1 divides p to the power n minus 1. Right? Why is it so? As I can write p to the power n minus 1 as p to the power some m times d minus 1. So I can write this as p to the power m minus 1 times p to the power m into d minus 1, and so on till p to the power m plus 1. Right? Similarly, in the exactly same way, I can say that t to the power p to the power m minus t must divide t to the power p to the power n minus t. Clear? Now, E contains all the roots of t to the power p to the power n minus t. Right? Now, because recall that E is the splitting field of t to the power p to the power n minus t. Right? Therefore, all the roots of t to the power p to the power n minus t is in E. Therefore, all the roots of t to the power p to the power m minus t is also in E, because t to the power p to the power m minus t divides t to the power p to the power n minus t. Right? Also, since t to the power p to the power m minus t has no repeated roots, we have seen such arguments previously, and all its roots forms a subfield of E, in this case of order p to the power m, we are done. Right? Therefore, what do we conclude from here is that if the order of E is p to the power n and we are given some m which divides n, then I can talk about the existence of a subfield of E of order p to the power n. Clear? Getting my point? Fine. Therefore, in fact, what we have concluded is something very important, that the if E has a every finite field of order p to the power n has a unique subfield of order p to the power n by this construction itself. Right? Why do we get hold of such an observation? You always need to come up with observations when you are going through a proof. Okay. Observe the following. Okay. Um, Observe the following. Okay. Suppose E is a field extension of some field f such that the order of f is let's say p to the power n. Okay. Then what should be the order of the multiplicative sorry, the order of the multiplicative group of f? It should be of order p to the power m minus 1, right? Because this is basically the collection of all units of f, and every non-zero element in a field is unit. That is something we know, right? Now if alpha is a unit in f, then that implies that alpha to the power p to the power m minus 1 must be 1, right? We know this. Why? Because recall in groups, if x is an element of a group G, then x to the power the order of G is 1. Obviously, we assume the order of G is finite, right? So alpha to the power the order of f cross should be 1, right? But what does that mean? That means that alpha to the power p to the power m must be equals to alpha, which means that alpha is a root of, or rather you do not even need this. Okay, this immediately doesn't imply that. I'm sorry, but this implies that alpha is a root of t to the power p to the power m minus 1 minus 1. Sorry, m minus 1. I'm sorry, m minus 1 minus 1, and hence a root of t to the power p to the power m minus t. Right. Therefore, what do we conclude from here? Thus, if order of E is p to the power n, then there exists a unique subfield of E of order p to the power m when m divides. Got my point? Okay. Now, in fact, uh, these finite fields are actually uniquely determined. Okay, we can actually talk about the uniqueness of these existences, and there is also one important observation about multiplicative group of a finite field. We can actually show that it's cyclic. Okay, that the multiplicative group of finite field can actually be shown to be cyclic. Yeah. Okay, but I was intended to do it in this lecture itself, but you know, I'm not thinking of that to do in this lecture. Rather, let's just end this lecture, or rather should I talk about that in this lecture? Okay, let's talk about, let's complete at least the multiplicative group part. Okay, then in the next lecture we will start with the uniqueness, and then we will be moving on to a deeper notions of irreducible polynomials. Yeah. Okay, fine. Wait a sec. Okay, so this is a theorem. Let f be a field, then let f star be f minus 0. Then any finite subgroup of f star is cyclic. Okay, got my point? That if f is a field, then any finite subgroup of f star is cyclic. So there, what does this immediately prove? That if f is a finite field, then that would imply that f star is a finite subgroup of itself, and hence is cyclic. Clear? Fine. Yeah. So the proof of this is quite simple. Proof. Okay. Suppose h is some finite subgroup of f, such that the order of h is n. Okay. Now observe the following. F is commutative, right? What does this mean? This means that f star is commutative. This means that h is a finite abelian group. Once it is a finite abelian group, what should struck in your mind? The structure theorem of finite abelian groups, right? Therefore, by the structure theorem, recall that I can write H to be isomorphic to a product of cyclic groups, right? Such that d1 divides d2 divides so on till dk minus 1 divides dk, right? And d1 times d2 till dk will give you n, right? Okay, 1 second. Right. Okay, got it? Fine. Now, whenever I choose an element x in H, what can I say? That x to the power dk should be 1, right? Clearly, this implies, so this immediately follows from here. Do verify. It's a very easy verification, right? Because x to the power n should be 1. Right? Therefore, x to the power d1 times d2 times dk should be 1. Each of these d1s, d1, d2 till dk minus 1, all of them divides dk. Okay, check through, right? Therefore, every element of H is a root of the polynomial t to the power dk minus 1, right? So, if n is less than or equal to dk, then this should imply n is equal to dk, k should be equal to 1, or dk should be equal to, or n should be equal to d1, right? Which immediately implies that H should be isomorphic to Z upon D1Z, which is isomorphic to Z over NZ, which is isomorphic to Zn, and hence it is cyclic. Got my point? Right? It's a very easy verification. So if I talk about a finite field of order p to the power n, then the multiplicative group is isomorphic to. So what do we conclude from here? Conclusion: if E is a finite field of order p to the power n, then its multiplicative group should be isomorphic to Z mod p to the power n minus 1. Why is it so? Because I can immediately do it from the previous exercise, that previous theorem, sorry. It should be isomorphic to Z mod the order of E cross times Z, and the order of E cross should be Z mod p to the power n minus 1. Yeah. And there's another easy conclusion from here. This proves that E star should be of the form 1 alpha square till alpha to the power p to the power n minus 1 for some alpha. Right? Okay. So let's end this lecture here itself. In the next lecture, we will come up with detailed analysis of irreducible polynomials and various checks of irreducibility. Right? And that will be the end of this series of lectures. And in the next lecture, I will also talk about the notion of uniqueness of finite field. I will rather start with the notion of uniqueness of finite field. Then the talk about on finite fields will be over, and then we will get on to the notions of irreducible polynomials. Okay.